everyone. So this presentation is about single crystal manufacturing metrology in an industrial scale as well as an academia scale. So we will present the travel from an ingot to a wafer and keeping control over lattice directions, keeping control over lattice constants, keeping control over the shape of the wafer, and all this will be content of this presentation. So let's get it on. First of all, I would like to allude to the market drivers in this industry. So we see a number of industries growing 2 digits like power GaN for inverters, for electric cars, or the silicon carbide industry, also for power electronics, and photonics is going steep these days. All these industries rely on perfectly cut crystals called wafers in our society. So these wafers, they are cut from ingots, so-called big lumps of crystals that are grown in a more or less complex way depending on the crystal grown. But all of them have in common that they need to be cut in the right way. So here's where we want to add additional value. So if we look at the manufacturing landscape, we are right at the beginning, just after the precursors are molten in the crucible, and a big ingot, for example silicon here, is created, where we are with our MRDXL products already, but we added now this new instrument suite to deliver more value to these clients in a more complete picture. Now, what have we acquired in terms of products? We have 2 compact systems here, the SDCOM, the DDCOM. These are systems that also would fit in an academia setting, if you like, next to the Omega Theta, which is also suitable for academia because it can offer a very large range of applications. But for industry, we have even larger systems called wafer XRD 200 or XRD 300. And for example, this end control system for wafer can give you about 3,000 to 4,000 wafers throughput per day. While the XRD OEM is a tool that can be integrated into grinders, into wafer source, into anything that processes your crystal. And there are examples from companies like Studer, who have already incorporated this into their product portfolio. Now, what are we talking? I alluded to parts of the process. So we have, for example, crystal growth in the Strachowski process, where you add polysilicon into a big crucible. You come with a seed crystal to a slightly undercooled melt, and you pull out a big ingot, which is a science in itself. But once the ingot is pulled, then you have this large lump of crystal that needs to be ground to a cylinder shape and needs to be trimmed. The flat needs to be ground at the right position. The wafer needs to be sliced. And all these manufacturing steps need careful control over the crystal direction in respect to the cutting surface. Now there's additional steps called wafer rounding, the lapping, the etching, the polishing, and inspection. And I'm going to show you how our portfolio now looks like. We have these multifunctional semi-manual tools that you can use in all those steps where you need control over the crystal orientation. Then we have automation tools for the end control that give you high throughput and additional metrology like conductivity, like shape analysis. We have our tools that we use so far in the semi-industry in XRD, that is the MRDXL, and the MRD line for the, let's say, high-resolution end control of the wafers. And of course the Aries that is typically bought for the feedstock analysis to have the right phase in there. And we have smaller systems for the polishing and for the wafer etching, bath control. Here, the OEM module has a special setting, if you like, because this is integrated in tools that other people manufacture and serves there as an orientation control before grinding, before sewing, more or less in situ. And yeah, summarizing the key benefits, just for those who are short in time, is the uptime is more than 99%. the transfer technology enables not only to measure accurately, but also to move this crystal on this reference frame into your cutting tool to preserve the orientation analysis that you have done also for your actual cutting process. It's a versatile range, and we offer precision down to 0.003 degrees. Now that's quite an achievement that is so far only possible with the theta method, but the theta method cannot do 5 seconds a sample, and this is what we combine here. It's an easy integration into the process line. We have a lot of experience with Freiberg to do that, so we are in close collaboration, and the absolute measurements eliminate all kinds of calibration. So here you benefit from this fundamental property of X3D. Now let's have a look further. The method description is here in 3 pictures. So in one picture you see the wafer is rotated. There is a diffraction pattern generated that you see in the center. And from this pattern, from the information that is latent in there, we can get the full crystal orientation of the wafer, so the direction of the offcut and its magnitude. The application output is of course also designed to serve operator specifications. So it's if you have an operator, he or she will see a very easy software interface. And of course you can also integrate all these values into your MES, SexGem system, or whatever automation protocol you're running. Now, orientation transfer. Some words about this. So you can see there is a sort of a frame, and this frame here, it will contain several crystals, and each of these crystals is in one of these shells. And you can see the software tells you how far to turn the screw in order to orient the crystal exactly in the right way. Now, once you have oriented all those stories here in this frame, you can add the sewing beam and you can glue it, and that will finally lead to the picture that you see here on the left side with the silicon carbide ingots. I think these are lined up all for the wafer saw to go in parallel into it. Accessories are important. All these accessories allow you to have an ease of use, a failure or a mistake-free operation. So there are no mix-ups, and there is a clear transfer possible from the, for example, seed orientation measurement to the Tucholsky growth setup. There is a clear transfer possible from let's say, here the silicon carbide boule to its reference plane, to the actual dicing device. And also here you can see when you have already done and ground the notch, you can check whether the notch is in the right position and do this with the necessary accuracy. Yeah, front end of line, there's a few options also here for those ones who buy silicon carbide or other crystals and rely on, let's say, expensive processes. They might want to know whether their supplier is actually delivering what he promised. So that is very good for the entrance control. The omega theta offers also rocking curves on 300 millimeter incidental orientation control. And of course, there is various more options, like you can imagine that wafer splitting for laser bars would also benefit from a clear orientation control, or whether the flat is really at the position where the manufacturer has promised. Now, the rocking curve option I talked about is shown here. You can see we have also XY tables. And these XY tables can take large ingots, can take individual wafers. There is height sensors. There is additional shape measurements if you wish. And you can see the full width at half maximum is pretty low. That is measured. So that means the optic is also capable of doing a good job for the actual quality control here. Now, again, the key benefits: uptime, transfer technology, the precision, and the combination of all three within the 5 seconds per sample that is achievable, for example, on silicon 100. Integrate it, don't calibrate it, use absolute measurements, and benefit from the value that we generate for you. Thank you.